Okay, so this is our last section in Unit 2. Our test is coming up Thursday, Friday. Okay? Potentially we would have a Wednesday night study session, but it would be late, like 7:30. But that's only tentative. Okay? Mr. Griebel and I have to see if it works in our schedules or not. And with it being Wednesday, it's a lot harder to do. So we'll do our best, but it's a maybe right now. Okay? We're going to talk about inverse trig derivatives, and I'll tell you, right now it kind of looks scary. It's not. And you're not going to have to memorize all 6 of the inverse trig ones, okay? So first of all, I made a mistake when I typed this. This does not pass the horizontal line test. Could you go ahead and cross out vertical and write horizontal for me? Okay. Y equals the sine of x does not pass the horizontal line test. And the horizontal line test tells us if our function has a inverse. Well, we've already talked about inverse trig in pre-calculus. So how is that possible if it doesn't pass the horizontal line test? Well, if you remember back to pre-calculus, what happens is they cut out a portion of y equals the sine of x to where, yes, it does pass the horizontal line test, and then they reflect it about y equals x. So this is the graph of inverse sine. And if you recall, arc sine is the same as inverse sine. Okay, we have the 2 different ways to notate it. Okay, you'll see this a lot more often, so I'll try to use that more, but you'll see both. Okay, yes.
Isn't that kind of like
tangent? We'll look at tangent, but tangent extends on forever and it has asymptotes.
Oh, it stops.
Yeah, this stops. Yep, these are like endpoints right here. Okay. Same thing with cosine. Y equals the cosine of x does not pass the horizontal line test. But if we concentrate on just this red portion, it would. And so when we reflect that red portion about the line y equals x, we get this graph right here. Okay? You're not going to need to know the graphs. I just want you to have that background information. Okay? And then the same thing with tangent of x. We know that the tangent of x repeats over and over and over and over and over again. And so if you have more than one of those tangent snakes is what I'll call it, it wouldn't pass the horizontal line test. But if we just pick the one that goes through the origin and we flip it across y equals x, we get this graph right here. This is actually a graph that will become very important, okay? So having this in the back of your memory is not a bad idea. But the visualization of this is tangent, okay, reflecting it for inverse tangent, okay, it looks a lot, it looks a lot like what happens with a cubic and a cube root function, okay? So what happens if you turn it to the back of your piece of paper? We have a very, very specific domain and range for our inverse trig functions. And this is something last year in pre-calculus we worked with quite a bit, okay? If we had an inverse trig function, we had to be very careful about the quadrant we got our answer from, if you maybe remember that back from January, okay? But what we are going to do, we are going to take these, and I want to talk about what each of their derivatives are, okay? What are we in Hintel? 51?
Yeah.
Okay. So I am going to show you where the rule comes from. What I am about to do, you will not have to regurgitate. Okay? I'm just showing you the why behind the rule. Okay? If y equals the inverse tangent of x, do you see where we do have like let's do some calculus? Okay? means x equals the tangent of y, right? Okay. Well, if we're talking about Trey, we're talking about the study of triangles. So if we have an angle y, then its tangent ratio is x over 1. Right? And how do we find the hypotenuse? Okay, a squared plus b squared equals c squared. So that would be our hypotenuse. Okay. Now, some of us need a little bit more practice with our implicit differentiation. So let's do that. Okay. So if we take the derivative of x equals tangent of y, because remember that is our definition of our inverse, right? Well, what's the derivative of, oh, that's not how I should write it. D dx should be better. Okay, sorry about that. What's the derivative of x? 1. And then the derivative of tangent y?
dy.
Secant squared y dy dx. Okay. Never forget that chain rule, that's right. So if we want dy dx by itself, we would have to divide over secant squared y. And I would be happy with that, okay? But let's talk about what it means in relationship to the triangle that we drew, okay? I'm going to flip-flop this here. dy dx. 1 over secant squared, do you agree, is the same thing as cosine squared y?
Yes.
Okay. Well, let's look at our triangle over here. Here is y. Our cosine ratio is adjacent over hypotenuse. Would you agree? Cosine is adjacent over hypotenuse. So in this triangle, the cosine adjacent over hypotenuse would look something like that. 1 over the hypotenuse. Okay? And since it's cosine squared, that square root goes away. Okay? I am not expecting you to be able to regurgitate this, but this is where this formula comes from. Okay? What I need you to be able to do is when you see the derivative of inverse tangent, you are going to know that it is 1 over 1 plus x squared. Go ahead and write that first. X squared plus 1, 1 plus x squared, doesn't matter. Yes or no, does it matter?
No.
No. Okay. Okay, go ahead and copy down sine and cosine first after you get the inverse tangent. So inverse sine and inverse cosine derivatives. Inverse sine and inverse cosine derivatives. Do they look kind of the same?
Generally.
Except they're opposite, okay? Their numerators are opposite. So if you know inverse sine derivative, you know inverse cosine derivative. And guess what? These 3 are the 3 I need you to remember. These other 3, if they appear in your homework, you'll have this sheet to help you, but they will not appear on a rule quiz or a test. Because they wouldn't appear on the AP test, so I'm not going to force that on you. Okay? But inverse sine, inverse cosine, and inverse tangent would be the 3 I need you to remember for a rule quiz and a test. Okay? Luckily, inverse sine and inverse cosine are just opposites of each other. So if you know one, you know the other. sure yours look exactly like mine. If you don't have the rule copied down correctly, you're not going to do your homework correctly. Okay, so be very diligent about the details here.
Two votes said Julia. We probably won't accept it.
That is a problem. That is a problem. All right, so let's look at our first example. You have a box down below for example 1. Okay, and what's nice, all of your rules are right above these example boxes. Okay, so we have an inverse tangent. We have arctangent. So when we talk about the derivative, we know that the derivative of the arctangent is 1 over 1 plus x squared. But do we have arctangent of x? No, we have arctangent of 2x. So we have 1 plus 2x squared. Say it louder, Celine. Times 2, because we have a chain rule. 2x is inside arctangent, so we would have to multiply by its derivative, 2. So what we have, just to make this look a little bit prettier, am I fine with you leaving it like this? Yes. But we do have 2 over 1 plus 4x squared. Because 2 squared is 4.
But then, why is the squared still?
Because 2 is squared and x is squared.
Okay.
But like I said, if you leave it like this, I have no problem. As long as you're using, I can see that you're multiplying. Okay? And that's it. That's really all I'm going to ask you to do is find these derivatives. Okay?
That's done.
Huh?
Moving on.
Moving on. Example 2. Example 2. I'm like giving you time to write these down, but they're already written down, aren't they? Okay, so arc sine of radical x. Arc sine of radical x. When we take the derivative, we have the arc sine derivative rule is 1 over radical 1 minus x squared. However, instead of x, inside of arc sine, we have what?
Radical
Okay. But our work isn't done because we have a composition. We need to multiply by what? 1/2 x to the negative 1/2. Okay, because that would be the chain rule. Remember, square root of x is the same thing as x to the 1/2. So when we apply the chain rule, the derivative of radical x would be 1/2 x to the negative 1/2 with that power rule. Okay. So you can rearrange that to look prettier, or you can leave it like that. It is fine. Can I answer any questions so far?
On the bottom,
Mm-hmm.
with the 2, like the exponent of 2 and radical x, just make it x.
Yeah, so if we wanted to make this look prettier, we would have 1 over the square root of 1 plus x multiplied by that, and that would be fine. Like if you had that in your answer because you did that in your head, I would have no problem with that. Okay. All right. How about you work together for example number 3? You have the rule up right above there, kind of catty corner, but above. Okay, work together to come up with the derivative for example 3.
You just have to apply the x squared plus 1.
All right. We're getting a little restless, so I'm thinking that maybe you're done. Okay. Our derivative. Heidi, what do you have back there for pod 5?
We have 1 over the absolute value of 7x squared plus 1 times equal 7x squared plus 1 squared minus 1 times 4x.
Like that? This is what pod 5 has. Do you agree? Good. Because it is right. Good job. Okay. All right. Questions before we move on to example 4? Some of you are already working on it, I see. That is the issue with guided notes. Okay. The example number 4. What is happening in our function? We have a product, which means we need to use the product rule. And if you're one of those people who like to kind of make notes of what we need to do, remember our product rule is f prime times g plus f times g prime. Okay, so derivative of our first function. So we have 2x arc cosine of x plus x squared times the derivative of arc cosine of x is negative 1 over radical 1 minus x squared. Right on? Okay. What I'd like to do in our last 10 minutes of class, I don't know if it'll take the whole 10 minutes, but I do want to pass back your quizzes and talk about those from Monday. Yesterday, our time pretty much got taken away from us. Okay. And then I have some other things that I probably should hand back to you. Okay.